Okay, so our last speaker before lunch is going to be Lapji Lau, and he's going to talk about graph decompositions and unit games.
Thanks for the organizer for the workshop. I want to talk about two results that come up from our study of the unit games problem. The first one is joint work with my student. With my students Vedat, and the second result is also joint work with Lima and Cheyenne. Okay, so our original motivations for studying the unit games problem is to consider unit games on graphs with many small eigenvalues. It is because we know that for graphs with few small eigenvalues, we know how to solve unit games effectively using the eigenspace elimination technique of Kohler. Sometimes motivations and results don't match. We couldn't solve the problem in such generality, but we ask what are some graphs that we know that have many small Laplacian eigenvalues. And in fact, I think the only well-known graph class with such property is graph without KR minor 3. It's KR minor 3 graphs and bounded genus graph. So, and then we ask the questions, can we solve unit games effectively on such graphs? Okay, so that was our first question. So before I talk about what is unit games, maybe we just focus on the simplest interesting case, the maximum cut problem. So the maximum cut problem we all know is we have an undirected graph, and then we just want to find a partition of the vertex set into two parts and maximizing the number of edges between the partition. Or equivalently, you can think about, I want to find partitions to minimize the number of edges on the same side. Or if I remove such edges, then the graph becomes bipartite, and then I have a max cut. Okay, so I think about the second version, the mean uncut problem. Okay, I'm given a KR minor 3 graphs, and I want to solve the mean uncut problem. What do we know about mean uncut? It's a classical result in 75 by Hadlock, that if you are given a planar graph, then we can solve max cut and so mean uncut exactly. And in general graphs, there's this result SDP approximation algorithms by Cherka, Makarichev. There's a log-n approximation, square root log-n approximation. I don't know, as far as I know, there's no known approximation algorithms for KR minor 3 graphs that do better than the general square root log-n approximation. So then we ask this question, and then with Vedat we show that for KR minor 3 graphs, we have an order R approximation, and then for graphs with genus at most G, we have a log G approximation for mean uncut. So I want to show you the proof of this result.
Are these NP hard? Okay.
I would think so. I mean, this graph with genus G, every graph, like when it is high enough, it is NP-hard.
So the mean uncut has some connection to multi-cut, no? Or is it?
You can use multi-cut, and multi-cut has a better approximation for KR minor 3 graphs. But then you have to do this reduction from your original graph to some label extended graph, and then you lost the KR minor 3-ness. So this is actually the technical issue that we have to handle, that we cannot work on the label extended graph. So let me start. We just write an LP relaxation instead of SDP relaxation. We just write an LP. We want to find the minimum number of edges to remove so that the remaining graph is bipartite. This is the mean uncut problem. And we just write this LP. And we want to minimize the total cost of the edges that we delete. And then we want to make the graph bipartite. We want to destroy all the odd cycles. So for each odd cycle, we want to remove at least one edges for all odd cycles C. And then we want this to be non-negative. So this is the LP relaxation that we use. I think it is known to be exact for planar graphs. But I don't think we have an efficient rounding algorithms for planar graphs. I don't know, maybe there is. So this LP is exact for planar graphs, but if someone gives you a solution, I don't know how to round it to a max cut.
It's not integral.
It is.
Could be a combination of integral solution.
So you don't want to use some like
Solution need not be
isolation
integral,
limit
it's
No,
style?
but
tied
the
to the
solution.
integral.
Okay, I see. So there are multiple. What was it?
So maybe I can say something about this. This LP has exponentially many constraints, but we can solve it effectively using the ellipsoid algorithms, using a shortest path algorithm as the oracle. I think maybe many of you know, but I want to bring up this point, like how do you solve it? If you have an edge UV, what we can do is we make two nodes for each node. Let's say U plus and U minus, V plus and V minus, and then we draw such an edge. And then there's an odd cycle in the original graph, if and only if there's a path from V plus to V minus.
Like less than.
Hmm?
This is a path of like less than 1 or something like that, right?
Right. And then if we want to check whether this LP is satisfiable, we just need to check whether the shortest path from V plus to V minus is at least 1 for all V. So if it's satisfied, then it's satisfied this LP. And I want to bring up this point because this is how people usually solve unique games, by constructing this label extended graph. So for each node, depending on the alphabet size, you create multiple copies of the same node. But I just want to add a remark that we cannot do this for our problem, because even if you are given a planar graph and you construct this label extended graph, it could have an arbitrarily large minor. Okay, so we restrict ourselves to work on the original graph. So what do we do? We use this standard and powerful tool in solving problems in KR-3 graphs, low diameter graph decomposition. It is used in actually many algorithms to design constant factor approximation algorithms for many problems. This one is closest to our work. They use it to solve the small set expansion problem, which is known to be closely related to unique games. 7 authors, and I think 6 of them are in this workshop. And we use the following version of the low diameter graph decomposition. It is not the original form. It is just a very simple form. The original paper is a very nice paper, and they prove much more, not just low diameter graph decomposition, but also padded decomposition and with stronger properties. What is low diameter graph decomposition? We are given a weighted graph, so each edge has a length WE, and then given any parameter delta, we can find there exists a distribution of partition such that each edge is cut with probability. If it is a KR-3 graph, it is cut with probability at most big O of R times WE divided by delta. And after cutting the graph, we have this property for sure. The diameter of each cluster is at most delta. The diameter means it is a little subtle. There are different definitions of the diameter, but it means for every pair of nodes in one part, the distance in the original graph is at most delta. There is a stronger version that even on the induced graph, the diameter is at most delta. We would actually come back to that point.
So the distance measured by W?
Measured by W, by the length function. Okay, so we are going to use this. So how are we going to use it? What do we want to solve our problem? We want to cut the graph into bipartite components. What do we know? We don't know how to cut into bipartite components. We only know how to cut into low diameter clusters. So what do we hope? We hope that low diameter components would imply the graph is bipartite. So why it should be true? The most natural approach is you set the length of each edge to be the fractional solution. You solve the LP, you look at the XE, and then assign it to be the length of the edge. And then what do we write in the LP? We said that for each odd cycle, it is long. The total length is at least 1. So suppose we can say that in such a long cycle, there exists a pair of nodes that their shortest path distance is greater than 1/4. Then we are good. Then we can run the low diameter graph decomposition with delta equal to 1/4 and cut the graph, and then some pair of nodes in the odd cycle would be separated. So that odd cycle would be killed. Okay? So if we can do that, then that would be good. And then the expected cost would be big O of our LP. It is because what is the expected cost? The expected cost is sum of the cost of each edge, the probability that it is cut. But the probability that it is cut in the low diameter graph decomposition is just big O of R times WE divided by delta. We choose delta to be constant, and sum of CWE is exactly the LP. Now we set it to be XE. It is exactly the LP value. So that is our plan. But the hope is not always true. For example, you consider this graph. I have an integral solution. I choose these 3 edges to be cut, but the shortest path distance between every pair of nodes is 0. You always have some 0 edges to go around. It is a low diameter cluster in the graph distance sense, but it is not bipartite. You may think that it is a silly example because we already have the integral solution. We just need to pick all the edges with 1, and then we are done. And what we observe is edges with large fractional value is the only obstruction to our hope. So we proved this lemma. Suppose all the edges, the fractional value is at most 1/2. Then for every odd cycle, there exists a pair of nodes with distance greater than 1/4. So this is the fix, and if this lemma is true, then we are done. We can first pick all the edges with fractional values greater than 1/2. We pay at most 2 times the LP cost, and then after that we run the decomposition with delta equal to 1/4, and then this analysis would go through. And then we cut all the revealing odd cycles. Okay, so now to finish the proof, I just need to show you the lemma, and I would do a proof by picture. It is a simple proof. So I give, if I'm given an odd cycle, I want to find a pair of nodes with large distance. If I find such a pair, then I'm done. I know that low diameter graph decomposition would separate them. So I start from a node. Let's say I look at this odd cycle. I look at, let's say, the midpoint, and then I compute the shortest path distance from U to V. If it is greater than 1/4, I'm happy. This can be separated. So if it is not true, it is at most 1/4. It breaks the graph. It breaks the cycle into 2 parts, and then at least one of them is odd. So let's say the left part is odd, and then I would focus on this part, and then let's say I look at the midpoint again, ask what is the distance. If it is greater than 1/4, I'm done. If it is not, and then I keep doing that, and then I ask this midpoint, and then if it is. But every time I'm doing this becomes shorter and shorter. If I cannot find such a large distance pair, then it becomes shorter and shorter, and eventually it becomes 1 edge. But this is an odd cycle. The sum of the length is at least 1, and then these 2 parts is at most 1/4. So this edge would have value at least 1/2. So that's the proof. So that's our first result, and this is true for KR-3 graphs. For bounded genus graph G, you just replace everything of R by log G, because we have stronger decomposition result for low diameter decomposition result for bounded genus graph. Okay.
Could you, sorry, why again was it bigger than half? I got it.
Because the odd cycle constraint said the odd cycle would be of total length at least 1. And then these two parts, the total length is at most 1/4. And
Yes.
Wait, so could we just ask for the short, instead of trying to do something recursive, could we just ask for the shortest odd cycle and then got a contradiction, or?
yeah, maybe you can also do it. Okay, so now maybe I can tell you what is the unique games conjecture. Uwe has already told you about it. I just consider a special case. This special case is tooling with alphabet size R. So we are just given a set of linear equations, xi plus xj is equal to Cij modulo R for some R. And we are given a bunch of such linear equations. And then the unique games conjecture can be equivalently stated as the following, that for every epsilon, there exists a large enough R such that for this two-lane R problem, it is NP hard to distinguish between the two cases. The first case is there exists an assignment that satisfies 1 minus epsilon fraction of constraint. The no case is no assignment satisfies more than epsilon fraction of constraint. So the general unique games problem can be reduced to the two-lane case. So for the two-lane case, we can just generalize the algorithms that we have and get exactly the same result for KR minor 3 graphs and bounded genus graph. Instead of cutting a cycle, you can define what it means to be an inconsistent cycle. You go along the constraint, that cycle has to be violated because the constant don't add up to be 0. And then you say it is an inconsistent cycle, and then you write an LP to cut all the inconsistent cycle, the same analysis would work. And then the approximation would be independent of R. The unique games conjecture is saying that the problem becomes harder and harder when the alphabet size becomes larger and larger. But for this particular problem, the approximation ratio is independent of R. And for general unique games that I haven't defined, but Uwe has defined, this cycle cutting algorithm doesn't work because whether a cycle can be satisfied, it's not only dependent on the cycle, it also depends on how you assign, depending on what value that you assign to the node. So, and then in those cases, we use the low diameter graph decomposition in this nice paper. They actually guarantee a stronger property, not only that in each cluster, the graph distance is small in the original graph, they are actually small in the cluster itself. So in particular, in each cluster, you can find shortest path tree, and then you can do propagation rounding exactly as in Gupta and Tower to solve the problem. So if you have a graph and then it has small diameter, then you can find a tree, and then you pick a node, assign some value to the node, and then propagate to the remaining nodes using the tree. And if it is short, then it works. And then we give a worse approximation ratio in the general case. If there exists an assignment that satisfies 1 minus epsilon fraction of constraint, we find an assignment that violates at most R times square root epsilon fraction of constraint. And then bounded genus graph, we got square root log G epsilon. So you can think of it as an refinement of some earlier SDP algorithms. For example, I think we match the result of Luca for this SDP approximation algorithms for unique games. And when the genus is smaller, it is a little bit better. Okay, so that is the first part of the talk. So now I want to motivate the second part of the talk. Suppose we want to design an algorithm to disprove the unique games conjecture. We can afford to delete 1% of the edges and do some graph decomposition. We know that unique games are easy on expander graphs. we also know that unique games are easy if each graph is of bounded diameter. So suppose we can delete 1% of the edges in the graph, and then in each remaining component, it is an expander, or if it is of low diameter, then we are done. So in fact, in some sense, it is also exactly what Aroa, Barak, and Stoyer does in their sub-exponential time algorithms. They do a graph decomposition procedure, and then after cutting 1% of edges, each component has few small Laplacian eigenvalues, and then they use Kohler's technique of eigenspace enumeration to solve each cluster. Okay, so now it seems graph decomposition is important to solving unique games. So we are interested in finding a good decomposition. So first of all, it is not true that if we are looking for the property of conductance and diameter, that's the best we can do. We cannot delete 1% of the edges and make every component of constant expansion. The best we can do is to make each component of conductance 1 over log n. Similarly, to the low diameter graph decomposition, we cannot make it constant diameter. We can only make it of diameter log n. For example, the hypercube is one such graph. So this log n loss is too bad for the unique games problem. Then our approximation ratio would be dependent on n, and we cannot disprove the unique games conjecture. So the questions that we would like to ask is there a relaxed property of low conductance, high conductance, and low diameter, so that we can actually prove a stronger decomposition result without this log n loss? Okay? And so what we proposed is
Is it high conductance or low diameter, or is it both?
each property would be good enough.
Either one.
Or, yeah.
Yeah, or. Okay.
But we can't get either of them.
But we cannot get either of them. So the property that we propose is to study effective resistance. So we think about the graph as electrical network. Each edge, the edge weight, instead of thinking of it as the length, it is the conductance of an edge. Or you can think of it as the resistance. Resistance is 1 over WE. And the effective resistance between two nodes, U and V, is defined as the potential difference between the two nodes. If we inject 1 unit of current to U and extract 1 unit current away from V. So there are different ways to understand it. It is called effective resistance because you think of the whole graph as a big resistor. You ask the question, if I inject 1 unit of current in U and take 1 unit of current away from V, if I think of the whole graph as a big resistor, what is the effective resistance? So that is the potential difference between the two nodes. So that is one intuition. And another way to think about it is the minimum energy to send 1 unit of flow from U to V, where the energy is defined as sum of the resistance times the flows square on that edge. Okay? So what do we know about effective resistance? So first of all, we can see that it is a relaxation of the two properties. If the distance between two nodes is small, the effective resistance between them is also small. It is very easy. We just send 1 unit of flow from U to V using the shortest path. And it is also known, maybe it's not as easy to see, is if I have a constant expansion graph, then the effective resistance between any pair of nodes is at most a constant. So the two properties, you can think of effective resistance as a relaxed property of low diameter and graph expansion. Okay? And intuitively, it is not a bad relaxation because usually when we think about a graph having low effective resistance between 2 points, we think of the graph as having many short disjoint paths connecting the 2 points. That's why the effective resistance is small. That's how you can minimize the energy by sending the flow along different routes to V. Okay? Or maybe I give some more motivations about effective resistance before I state our main result. So traditionally, effective resistance is related to parameters of random walks and random spanning trees. It is exactly proportional to the heating time of two nodes. It is closely related to the cover time if we do random walks. And we also know effective resistance of an edge is exactly the probability of an edge in a random spanning tree. And more recently, effective resistance is useful in surprising ways in different problems. It is useful in graph specifications, in computing maximum flow, in finding thin tree, and also in fast generation of random spanning trees. So this last work is closely related to us because they also want to decompose the graph into cluster with small effective resistance such that the cover time is small. And I think maybe it is also a natural question in itself. We want to do graph partitioning, but we use effective resistance as a distance measure. It also satisfies triangle inequality. And if you think about maybe I do graph partitioning in a social network, effective resistance is a good measure. If two people, they have 10 common friends, they are closer to two people who have only one common friend, and instead of just using the shortest path distance. So what our main result is about graph decomposition using effective resistance for any weighted graph and for any large enough constant, there exists a partition of the vertex set such that the resistance diameter is small, meaning that if you look at each cluster, look at every 2 points, the effective resistance is at most delta. Delta, you think of it as a large constant, times n divided by the total weight in the graph. And there are only few edges between clusters. The number of edges that we need to remove is at most a constant fraction of the total weight. Maybe you think of delta as 1,000. So we just remove 10% of the edges. 1%.
Again, this is effective resistance in the induced subgraph, not the original graph?
In the induced subgraph, yeah. It is a stronger notion. Okay.
And what's quantification of K? So K is
Some partition. We don't restrict on K.
what I'm confused about is if you multiply all the weights by 2, like that delta n over WE, like it doesn't feel like it's homogeneous.
Yeah, it is not, because if you give me a graph where every edge has very small weight, which means very high effective resistance, high resistance on such an edge, then the diameter bound we can hope would be weaker. So maybe let me give you a concrete example. Let's say we just restrict to unweighted D-regular graphs, and then sum of the edge weight would be exactly equal to E, number of edges in the graph. Then we can decompose the graph into components such that each component is of resistance diameter constant over D. And we only delete a constant fraction of edges. So I want to say that this is actually the optimal thing to do in terms of these electrical properties, because if you have a graph with maximum degree D, the effective resistance is at least omega 1 over D, because you just have a mean cut and you need a lot of energy to cross the cut. And a constant expander would give you resistance diameter 1 over D. So although we cannot decompose the graph into constant expansion graph, but we can decompose into components with the same optimal electrical properties. So that is the statement. I'm about to stop soon. So the main technical results that we prove to prove this decomposition is the following statement. we said that if you look at every cut, suppose you are given two nodes U and V, if you look at every cut separating U and V, if the number of edges crossing the cut is at least C times volume to 1/2 plus epsilon, it has to be greater than 1/2, a little bit, then the effective resistance is bounded by this. So maybe it is a little difficult to parse this equation, but I think the main point to notice is the expansion requirement is much weaker for large set. For large set, the conductance requirement is sublinear. Usually when you talk about the conductance, you say it's C times the volume of S. But we just say C times the square root volume of S is enough to guarantee you have a small effective resistance. So that is the main point. And then the proofs are not difficult. Both proofs are not difficult. The first proof is a little similar to what you do in Chicka's inequality. You just look at the potential vector, and then you look at all the level set. You said if you have good expansion on each level set, then the potential difference would be small. And then you use it to bound the potential difference between U and V. And then the square root would come out. And then the second result is just to keep applying the first result, keep cutting the graph, and because the conductance is sublinear, you would have a geometric decreasing sequence, and then you don't have this log n loss. So let me just end with two open questions. I think there are a few interesting questions that you can ask about this decomposition, but I just asked two. One is for the fast algorithms people. Can you compute this decomposition in near linear time? We can use Laplacian solver to compute a cut, and the total running time is m times n, but maybe you can do it in near linear time. And the other question is for the approximation people, are there some natural problems, non-trivial problems that we know how to solve it more effectively if we guarantee that the graph has bounded effective resistance diameter? So ideally, that would be unique games. Maybe propagation rounding would work better in such graphs, and then that would be good. But if it doesn't work out that way, there are some other problems that it would work. Okay, so I will stop here.
Time for some quick questions.
Can you give an example of a graph which is sort of has small effective resistance, but it's not a good expander?
Hypercube.
It's
Any
not a
transitive
constant.
graph, right?
Yeah.
Every transitive graph. Oh wait.
Three-dimensional.
Yeah, it's maybe more like hypercube is pretty good expander at some level. Maybe you lose a log factor, but 3D cube is.
Wait, I think that if every pair of nodes has effective resistance 1, it can't be more than some log off from expander. Isn't that right?
The three-dimensional has
Yeah.
whatever commute time and mixing time.
It is a relaxation of the two properties, but somehow it gives you more. If the diameter is large, you know that there could be many paths between them. So it's kind of an L2 relaxation of the two properties.
More questions?
Okay. It comes around back to this.
Okay, otherwise enjoy your lunch break. Stay safe. Keep your head down.